Now, putting this together, we can model and work with projections at any angle. So not just the horizontal, but those that are at a diagonal. So in this question, we know the initial velocity was 28 meters per second and the angle of elevation was 30 degrees. So I'll start by modeling those. This particle's been projected and I'll draw its flight path from its projection to its highest point, back down to when it hits the ground. Now the initial projection I can break into components. I can have the horizontal and the vertical, and we know how to label these components: 28 sine 30 and 28 cosine 30. And now we'll just go about thinking about this problem both vertically and horizontally. First, I'll get those variables for the vertical motion. I don't know the displacement, but I know the initial velocity is 20 sine 30, which equals 14. Final velocity is 0. Acceleration is negative 9.8 because I've chosen up as my positive direction. And the time, I don't know the time for it to get to the highest point. But I'm looking for the displacement, so just choosing the appropriate formula. V squared equals U squared minus 2AS plus 2AS, and substitute those values in. Okay, rearranging, S gives us a round value of 10. So the greatest height that this particle is over the ground will be 10 meters. So in part B, we're asked to find the total flight time for this particle. Well, the total time that is in the air is in between O and A, in between the origin and point A. Well, I know that the vertical displacement at point A is 0, so that's what I'll work with in the variables. So we'll set them up: displacement of 0, initial velocity of 14, just like we found before. Final velocity I don't know, and I might not need. Acceleration of negative 9.8, and the time I don't know, but that is what I'm looking for. So using those variables, S equals ut plus half at squared, substitute the values in, and it looks like I'm going to solve through factorizing. And that generates two results: t equals 0 or t equals 2.8257. T equals 0 actually makes sense because that's the point of projection. Time equals 0 when I initially projected this particle, and the displacement was 0. But it's not the point I'm interested in. The second time that displacement equaled 0 was when time equaled 2.8257, and that's the point where the particle comes back to the ground. So the total time of flight for this particle is 2.8257 seconds. And in this final part, we're asked for the distance OA. That's going to be a horizontal distance, also known as the range. So to work with that, I'll go for these horizontal components. I don't know the distance. I've got the initial horizontal velocity, 28 cosine 30, and the time that I found in the previous question, I'll keep in its exact form, 14 over 4.9. I'm going to use them in the horizontal displacement formula, which is S equals ut. Initial velocity multiplied by time, which gives us 69.282. Okay, so we'll look at a situation that's different in two ways. Firstly, this particle is projected from a point that is not on the ground. So I'm just going to start with a sketch, drawing O above the ground. The initial velocity is v, and the angle is unknown. So I've got those bits. 42.5 meters above the ground is where this particle's been projected from, and here's my flight path. If it impacts the ground, it's going to impact at the point A. The question told me something about that angle. It told me tan theta is 4 over 3. So if I use that to set up a right angle triangle, the angle, the opposite being 4, adjacent being 3, and Pythagoras lets me know that the hypotenuse will be 5. I can go ahead and generate expressions for sine theta, 4/5, and cosine theta, 3/5. Now these fractions I'm going to use in my calculations. Okay, let's go ahead and find these components, vertical and horizontal components of the initial velocity. Well, the vertical should be sine v, and the horizontal should be cosine v. Since I know the fractions, I'll just use 4/5v and 3/5v. Okay, now we're ready to start working horizontally and vertically and use our suvat variables. So let's start vertically with our suvat variables. We'll choose up as our positive direction since the initial direction vertically would have been up, which gives us negative displacement 42.5. We'll plug in the initial velocity. The acceleration as usual is negative 9.8 and the time is 5 seconds. We don't know the final velocity and we may not need to know. So plugging these values into s equals ut plus half at squared, I really just need to rearrange as the only unknown is that v value, that initial velocity value. Okay, so some expansion and some smart rearranging gets us a value of v, which is 20. V equals 20 meters per second. And that's the magnitude, the diagonal magnitude of the initial velocity. So in part B of the question, we've been asked to find the distance between O and A. So let's start by finding the horizontal displacement. We'll throw in our variables, unknown displacement, that's what we're looking for. The initial velocity was 3/5 of v, which we now know is 3/5 of 20. So that gives us 12. Obviously our acceleration is 0 and time is 5. So using s equals ut for the horizontal, we know that that's going to be 60. So the horizontal displacement is 60. But we'll ask for the distance. So that's this diagonal distance. So a little bit of Pythagoras should help us to calculate that diagonal distance. Okay, so we know that the vertical distance is 42.5 and the horizontal is 60. So a little bit of Pythagoras gives us OA of 73.527. Okay, and just one more to finish with. Here we've been told that a particle is projected from the point O with a speed of 35 meters per second and the angle of elevation is 30 degrees. The particle is moving freely under gravity. Find the time when the particle is 15 meters or more above that point O. So let's just set up the initial line of projection, the angle of elevation, and we can go ahead and find our usual components. I'm going to add this line, the 15 meters. So we want to know when and every time that it is exactly 15 meters above the ground, and then we'll try and find the time in between that. So we'll start vertically. So displacement of 15, initial velocity 35 sine 30, final velocity I'm unaware of, negative 9.8 since up is the positive direction, and we're looking for 2 times where this is true, where the displacement is 15. So we'll go ahead and substitute them into s equals ut plus half at squared, and this is a quadratic, so it should generate 2 separate values for t. Okay, just rearranging and solving, maybe punching that into your equation solver, and we get these 2 values, 10/7 and 15/7. So I'll just label these as the times when the displacement is 15 above the ground. Well, everywhere in between these 2 times, it's above 15. We can see that from the diagram. So me subtracting those 2 times lets me know how long this particle is higher than 15 meters above the ground. So that subtraction gives us 5/7. The particle was above 15 meters for 5/7 seconds, or 0.71 seconds.